Alright, in this video we're going to look at inverse functions. So the first thing to figure out is when do we actually have an inverse function. So for an inverse function we're going to say that a function has an inverse function if for each output there is exactly one input. A function that has an inverse function is called one-to-one, and so we've already looked at one-to-one functions in the past. And so why we might want an inverse function is we might want a way of going backwards. So for example, if we wanted to convert from Fahrenheit to Celsius and then convert back from Celsius to Fahrenheit, you can think of your function as Fahrenheit to Celsius and then the inverse function from Celsius back to Fahrenheit. Or you can think of a function as converting inches to feet, and then the inverse would take feet and convert it back into inches. And so we would want this one-to-one relationship, and we would want to go forwards and backwards for various applications. So we're going to look at it in terms of just some generic functions. So if you see f of a is equal to b, then the f minus 1, that's the f inverse of b is equal to a, or f inverse is called the inverse function of f here. Okay, and so let's go ahead and get started. So let's say that f of 10 is 7, then, so that means the function takes 10 to 7. The inverse is going to take the 7 and bring it right back to 10. So hypothetically, 10 degrees Fahrenheit would be 7 degrees Celsius. That's probably not true, but for the sake of argument, then 7 degrees Celsius would be 10 degrees Fahrenheit, and you'd have your function and its inverse. So the domain of f, 10 is in the domain of f, and that's going to be sent to 7, which is in the range of f. The inverse is going to start with 7, so that's going to be the domain of f inverse. And the range of f inverse is going to be 10, the destination, and that's what f inverse is going to do. So what we're going to be saying like a million times is the domain and the range are switched when you're considering a function and its inverse. So the domain and the range are going to be switched. The x's and y's are going to be switched. Okay. So we're going to take a look at a set of ordered pairs in just a moment. So let's go ahead and put this in here. So determine whether the following functions are one-to-one. If the function is invertible, which means it's one-to-one, find the domain of f and f inverse. Okay, so I have the function f defined as a couple of ordered pairs, 32, 0, 68, 20, 104, 40, 140, and 60. And this is actually some ordered pairs Fahrenheit to Celsius, so 30 degrees Fahrenheit is 0 degrees Celsius, 68 degrees Fahrenheit is 20 degrees Celsius, etc. The domain of f is going to be, and let's go ahead and knock this out, is this invertible? And the answer is yes. I do not see any repeating y, so that means it's one-to-one or invertible. There is also no repeating x's, so it is a function. The domain is going to be all the Fahrenheit values, which would be 32, 68, 104, and 140 from our set of ordered pairs. And the range is going to be Celsius. So that's going to be 0, 20, 40, and 60. So then for the inverse, we're going to take Celsius to Fahrenheit, Celsius to Fahrenheit, Celsius to Fahrenheit, and one more time Celsius to Fahrenheit. So then our domain is going to be the range of f, and the range is going to be the domain of f. Okay, so you just have your x and your y switched. And then we had one other example we're going to look at. We have the ordered pairs 1, 7, 3, 5, 2, 6, and 4, 7. Now we have repeating 7, so that means that it is not going to be a one-to-one function. And if it's not one-to-one, then it does not have an inverse function. There is no inverse function. there's an inverse relation, but the inverse relation is not going to be a function, so we're not going to be as interested in that. Okay, so that's we're going to look at sets of ordered pairs. We're also going to look at some graphs and determine whether they are one-to-one or not. So here we have x squared plus 1, and the question is this a one-to-one function? And so we've probably answered this question in the past using the horizontal line test, but we can go ahead and discuss it again. So here it is, and then I can pick 2 points. Here's 2, 5, and here's negative 2, 5. And I do have repeating y's. So if I have repeating y's, it's not going to be a one-to-one function. So this is a not one-to-one function here, and so that's it. However, what we might be able to do is we might be able to do some sort of restricted domain. And so, well, what if I get rid of the left-hand side here, okay? So if I get rid of the left-hand side, then I think I'm going to be okay. I think we're going to be able to pass the horizontal line test, which would mean we don't have any repeating y's. And so we are interested in that later on in math, especially when we're getting into the sine and the cosine and the tangent, your trigonometric functions. We might be interested in having an inverse function for various applications, but none of those in their regular form pass the horizontal line test, so we might want to do a restricted domain. So we're going to look at a more basic example here. So we're going to take this same graph here, x squared plus 1, but we're going to make a restriction on it. We're going to say that x has to be greater than or equal to 1. So we're looking at exactly the right-hand side, and so I think that's going to be just fine. That's going to be a one-to-one function. So it's going to pass that horizontal line test. So it does have an inverse. And we'll do a little extra here. So it is one-to-one. What I'm going to do is I'm going to write down some of the ordered pairs that I have graphed there. 0, 1, 1, 2, 2, 5, and 3, 9. Now, we're going to practice graphing the inverse. And to graph the inverse, all we have to do is switch the x and y. You're switching your domain and your range. And so that'll give us 1, 0. We'll plot that. And then 2, 1. Plot that. 5, 2, plot that, and 9, 3, and plot that. And so now we have the inverse graphed there along with the original function. And then I'm going to put in as a dashed line the identity y equals x, and it so happens that a function and its inverse are going to be symmetric about y equals x. Okay. Now, if you want to do a little bit more, I guess we can say this is kind of a preview of some of the other stuff we're going to do in this lesson. Okay, so f of x equals x squared plus 1. That's the same thing as x squared plus 1. Now, the y is going to be greater than or equal to 0, and we do have a restricted domain here. So what we're going to do is we're going to kind of follow what we did with those ordered pairs. We're going to switch the x and y. So now we have x is equal to y squared plus 1, and we're going to solve for the y. So we're going to subtract 1 from both sides, and then we're going to take the square root. Okay, so normally we'd get a plus or minus, but because of the restricted domain here, we're not going to have a plus or minus, and so our f inverse is going to be the square root of x minus 1, which is exactly the graph that we have here. This is the eyebrow shifted 1 unit to the right there, so that looks good. We were able to find the inverse function there. Again, we do not have any plus or minus because of the fact that we are missing the other half of the parabola, which would end up being down here. Okay, so moving along. We will mention the horizontal line test for reference. Okay, so I think we've had that in a previous lesson. So the horizontal line test says a function has an inverse function if any horizontal line intersects the graph at most once. So we've done a few examples of that. I guess we can draw a couple of pictures here. So here'd be a couple pictures. Looks like I'm drawing letters or something. So parabola, not 1 to 1. XOR looks like an absolute value, not 1 to 1. The S here is going to be a little bit trickier. It's not a function, and it's also not 1 to 1. So it does not pass horizontal line or vertical line test. So definitely not either one of those. The eyebrow, that is a 1 to 1 function. Okay. All right. So moving along, we're going to look at how to find an inverse given the fact that the function does have an inverse, and given the formula. And so the steps in the procedure here is to find the inverse function. The first thing we're going to do is we're going to replace f of x with y and switch x and y. We may not have to do this every time. If the function already is y equals, then we don't need to switch. We don't need to replace the fx. After we've switched x and y, we'll solve for y, and after we've done that, we're going to replace y with f inverse of x. So we're going to go ahead and I've changed the problem just slightly. Instead of y equals 2x plus 5, it's going to be f of x equals 2x plus 5. So we're going to find the domain and range of both f and f inverse. So here is f of x. So I've replaced the y, or I've rewritten it so we do this replace fx with y. So fx is equal to 2x plus 5. This has a domain of all real numbers. There's no denominators or square roots. So here we go. Y equals 2x plus 5. Switch x and y. And then we're going to solve for y by subtracting 5 from both sides and then dividing by 2. And then replacing y with f inverse of x. So there is our inverse function, x minus 5 over 2. That does not have, it does have a denominator, but it's 2, so we only got to worry about denominators with x's, and there's no square roots, so the domain is all real numbers for the inverse. Okay, the range of f inverse is going to be the domain of the original function, which is minus infinity to infinity, and the range of f is going to be the domain of f inverse. So I have a typo here. Sorry about that. This is just regular old f. Oops, I'm going to try to erase it. That's just regular old f. It's not f inverse. So that is my error. Sometimes I get carried away in the excitement here. Okay, so there's a real basic example. We're going to do a slightly more difficult one, and then maybe a little bit of a challenging problem. Okay, so same instructions. We're going to find the inverse function, and then we'll find the domain and the range of f and f inverse. So this time we're going to look at f of x is equal to x cubed minus 1. That does not have any denominators or square roots, so the domain is going to be all real numbers, negative infinity to infinity. We're going to replace fx with y, and then we're going to switch x and y. We're going to add 1 to both sides in the process of solving for y. So we add 1 to both sides in the process for solving for y. And then to undo the cube, we're going to take the cube root. And when we take odd roots, we don't do any plus or minus. Okay, so the cube root of x plus 1, that is what f inverse is going to be. The cube root is not a picky function, so the domain is going to be all real numbers. It's only square roots or even roots that have problems. Okay, so then the range of f is going to be, oh, I did it again. Sorry about that. The range of f, not the range of f inverse. Well, I guess it doesn't matter so much here because the domain of both f and f inverse is all real numbers, but we need to be correct. Range of f is going to be the same as the domain of f inverse, which is minus infinity to infinity. And then the range of f inverse is going to be the domain of f, which is all real numbers. Okay? So, pretty simple example. The next example is going to be a little bit more challenging, mostly because of the algebra involved there. Okay, so number 3, we're going to look at f of x is equal to x plus 2 over x plus 5. This does have a denominator with a variable, so we're going to set the x plus 5 not equal to 0. And that is going to give us a restriction of x cannot be negative 5. And so for our domain, it's going to be minus infinity to negative 5, union minus 5 to infinity, so we do have to hop over the negative 5, okay? All right, so we got the domain squared away. It's probably easiest to go ahead and find the inverse function and then find the domain of the inverse function, and then we can find the range of f and f inverse based off of that. Okay, so moving along, replace the fx with y, and then we're going to switch the x and y, and then we're going to clear the fraction, so we're going to multiply both sides by y plus 5. We'll distribute on the left-hand side and get yx plus 5x equals y plus 2. Okay, now I have drawn arrows because we have y's on both sides of the equation. So we don't want to do anything weird like divide by x or divide by y. That's not going to do it for us. That's going to introduce some fractions. That's going to be a mess. So what we would like to do is to pick a side. It doesn't matter which side we do. We'll get the same answer as long as we take the correct steps, and move the y's onto the one side, all the y terms onto one side, and then everybody else to the other. So I've decided to move the y's onto the left-hand side. So I'm going to subtract y from both sides. Now y is not a like term with yx, so I can't combine them, but I can write it as yx minus y. We still have 5x hanging out on the left-hand side, and that's equal to 2. Okay? And there are my two y terms. So we got them on the left-hand side. Now 5x is not a y term, so we're going to go ahead and move it over. So we're going to subtract 5x from both sides to move it over. Okay, so now we have yx minus y equals 2 minus 5x. Okay, and so here we do not want to divide by x. We don't want to divide by y. We don't want to do those things. What we want to do here is we got both terms have y. You have a yx and a minus y. They both have a factor of y. So what we're going to do is we're going to factor out a y. So it's going to be y times x minus 1. And then I can check to make sure that's actually true. Is that actually what it was before? Well, y times x, that's yx. Y times minus 1, that's minus y. So it's the same thing. Okay. So y times the quantity x minus 1 is equal to 2 minus 5x. The x minus 1 is attached to the y by multiplication, so therefore we need to divide both sides by x minus 1. Now f inverse of x is going to be equal to 2 minus 5x over x minus 1. Okay. Alternatively, if back over here, this step here, if we decided to move all the y's onto the right-hand side, we would come with an equivalent but slightly different looking answer. So, or f inverse of x would be equal to 5x minus 2. Well, it should be minus 2, excuse me, minus 2 over 1 minus x. Okay, either answer is fine. It just depends on what route you take. They are equivalent. To get the second form to look like the first form, you just need to multiply the top by negative 1 and then the bottom by negative 1. So if we did that, then we would have the same thing. Okay, so let's take those off. Okay, all right, so now you got your inverse, and your inverse does have a denominator, so it's going to have a restriction. So we're going to go ahead and find that. So the domain of f inverse, we're going to set x minus 1 cannot be 0, so x cannot be 1. So our domain of f inverse is going to be negative infinity to 1, union 1 to infinity. Now the domain of f is the same thing, the domain of f inverse, the domain of f inverse is the same as the range of f, which will be negative infinity to 1, union 1 to infinity. And then the range of f inverse, is going to be the domain of f. Okay, so we got domain and range of both f and f inverse. We got the original f of x and also the inverse function there. Okay, so let's go ahead and move along. So we'll go ahead and speed this up here. So this is just what we've just mentioned. So if f has an inverse function, then the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So for example, let's say that f is invertible function, meaning it's 1 to 1, so it has an inverse. And the domain of that is -3 to 17, bracket at -3, parentheses at 17. And the range is -11 to infinity. So the domain is going to be the -3 to 11, to 17. And then the range will be -11 to infinity. The inverse, we just switch the x and y, the domain and range. So you have to be a little bit careful. It's not 17 to -3 and infinity to -11. So you got to be a little bit careful. We don't want to do that. It's going to be switch the entire domain and the entire range. So it'll be minus infinity. Now I can't say it correctly. -11 to infinity, and then -3 to 17. So your domain of the inverse is going to be -11 to infinity, and the range of f inverse is going to be equal to -3 to 17. Okay, and so we have those same relations there. Okay, we're going to look at two other things. We're going to look at verification of inverses using composition, and then we're going to do a little bit of graphing a function and its inverse. So let's see what we got going on here. All right, so to verify that two functions are inverses, if they satisfy the following properties. One, the f composed with g of x is x, and two, g of f of x is equal to x. If both those conditions are met, then f and g are inverses of each other. If either one of those cases is not equal to x, then we just say no, they're not inverses. All right, so first question here is we want to verify the following are inverses using composition. So f of x is equal to 2x plus 5, and g of x is equal to x minus 5 over 2. So we'll find f composed with g of x, which is f of g of x, which is equal to f of x minus 5 over 2. And then your function f is going to take the input, multiply it by 2, and then add 5. So our input here is x minus 5 over 2. X minus 5 over 2. And so we have multiplication by 2 and division by 2, so those are going to absorb. And we have x minus 5 and plus 5, which is equal to x. All right, so we're halfway there. If I had gotten anything other than x, then we'd say no, they're not inverses. But we did get x, so we have to check the other way. Okay, so second thing is check g composed with f of x. So that'll be g of f of x, and f of x is 2x plus 5. What g does is subtract 5 from the input and then adds 2. So it subtracts 5 from the input and then divides by 2. Input is 2x plus 5. So we'll go ahead and work out the top, simplify it down. The plus 5 and minus 5 will absorb. And then we have 2x over 2, and then those will divide out, and we'll be left with x. So we got x both ways. So that is going to tell us that f and g are inverses of each other. It turns out that the inverses are going to be unique, but we're not going to address that proof in this video. But f and g are unique, so the inverse function is going to be unique. There's only one inverse function for a function if it does exist. All right, so we're going to look at, I think, two more. I think I only have one more in the notes, but I've come up with one more example for the video here. So number 2, we're going to look at f of x is equal to x cubed minus 1, and then g of x is equal to the cube root of x plus 1. So we'll go ahead and find f composed with g of x, which is equal to f of g of x and f of cube root of x plus 1. What f does is it cubes the input and then subtracts 1. So the cube and the cube root are going to undo each other, so that frees the x plus 1. And then we'll subtract 1, and we get x. Okay. Then we're going to do g of f of x. which is going to be equal to g of f of x, which is equal to g of the x cubed minus 1. And then g is going to take the input, add 1 to it, and then take the cube root. So the input is x cubed minus 1. We'll add 1 and then take the cube root. The minus 1 and 1 will absorb. And then we have the cube root of x cubed. The cube and cube root will undo each other. And so that will free the x. And so we get x both ways to the composition. So that tells us that f and g are inverses of each other. Okay, we're going to look at one more example here. So let's say we have h of x is equal to 3x plus 2, minus 1, sorry, and g of x is equal to 1/3 x plus 1. So we'll find h composed with g of x, which will be equal to h of g of x, which is equal to h of g of x is 1/3 x plus 1. So your function is going to multiply that input by 3 and then subtract 1. So we'll go ahead and plug that in. Order of operations, distribute the 3. So x plus 3 minus 1. And that gives us x plus 2. And x plus 2 is not x, so we say h and g are not inverses of each other. We don't even need to bother to check the other direction, the other composition, we're done. The answer to the question is they are not inverses because we got something other than x. Okay. All right. So the last thing we're going to take a look at is we're going to do a little bit of sketching. So we're going to look at sketching a graph and its inverse, and then we'll make the note that a function and its inverse are symmetric about the identity y equals x. Okay. So here we have we're going to graph f of x, f inverse, and then also y equals x. So we're looking at f of x is equal to 2x plus 5, and f inverse of x is equal to x minus 5 over 2. I'm going to make a little t-table for this. And I only need, realistically, I only need 2 points, but I'm going to do 3 points. If you remember graphing lines, then the y-intercept is 5, slope is up 2 over 1. We're just going to do a little t-chart to keep things simple. So I'm going to pick a couple of values, 0, 1, and 2. And we're just going to plug them in. So we get 5, 7, and 9. We'll go ahead and connect your dots, draw your line, and then also label it. Okay. Now to graph the inverse, all we got to do is take those values that we found and switch the x and y. So 5, 0, 7, 1, and 9, 2. We'll sketch that line also. And then also put in the identity after we label f inverse. And so the red here and the black here, they are reflections over the identity. And then this portion here is a reflection over y equals x as well. Okay. So both f and, well, it's not g, is it? Both f and f inverse are reflections over the identity y equals x. Okay. All right, so we're going to look at sketching one more. This time we're going to look at f of x equals the cube root of x plus 1, and f inverse of x is equal to x cubed minus 1. I'll make the argument that graphing x cubed minus 1 might be slightly easier to do than the cube root of x plus 1. They're about the same level of difficulty, but we'll go ahead and graph the inverse, and then to get from the inverse to the original function, we switch x and y. So it's going to be a very similar procedure. So I'm going to go ahead and use x and then x cubed minus 1. So that is your cubic function shifted down 1 unit. We'll go ahead and make the t-table so it'll make it easy to switch the x and y so we can graph the inverse. So we'll go ahead and use basically the same values when we graph the parent, but it's going to be the y values with 1 less. So -2 and -9, -1, -2, 0, -1, 1, 0, and 2, and 7. So we'll go ahead and plot those points, and there is our cubic function shifted down 1 unit. Okay, then we'll go ahead and label that as the inverse. Now to find the original function, we'll go ahead and switch the x and y from our t-table over there. I've also put in the identity y equals x. That's going to help us out when we're doing a little bit of sketching. Okay, so here's x and the cube root of x plus 1. So we'll reverse our table, -9 and -2, -2 and -1, -1 and 0, 0, 1, and 7 and 2. Okay. So when we're sketching this, I do see this part is kind of flat and curving away a little bit. So I'm going to try to do that same characteristic here. We are curving sort of slightly away, slightly away, maybe curving a little bit back towards, and then curving away and flat like that. Okay, so I'm going to go ahead and try that out here with my sketch. If I need to, I can pick some more points and just switch the x and y's. Probably I would throw them into the x cubed minus 1, so maybe I want to pick like, I don't know, like a half or something like that as another x value if I needed to, if I want to try to get a more accurate picture. Okay, so we'll go ahead and start sketching that. So there's that flat piece there, and then we'll do this kind of this middle piece, and then that final piece, and then label that as our original function f. So again, both f inverse and f are going to be reflections about the identity y equals x, and that will always be the case. Okay, so that concludes a brief 30-minute video of inverses and some things we can do with inverse functions, how to find them, how to find the domain and the range, how to graph them, so I think we're about done here.